Here we go. So, again, the idea is, and we've done this, our green board already has some of these, so let's just think, here's our big old green board, right, that we've soldered, our breakout board. In the middle is our launch pad, right? The 28379D. Okay, and technically that chip is that little square black chip in the middle of that red board. Okay. Now, we have these 80-pin connectors that we can use to get out to the world. Okay? So, stuff we've already talked about. Then, you'll see, my little chip that I soldered on for you. Right here's the DAN 28027 chip. Right down here is our IMU board. It's a little board, right, with headers. Right here's our IMU. It's called the MPU 9250, happens to be the name of it. Okay? Now, these devices are not, obviously, inside our processor. Okay? We need to communicate to these devices. Also, we have some other devices out there. Well, really just one other one. That's up here by our battery, our little coin cell battery. By the way, if I haven't given you a coin cell battery, just ask me the next time you're in lab or whatever. I got coin cell batteries I can give you. Right here is a chip called the BQ32000. And that's a little, they call it a real-time clock chip. That just means it's a little watch, right? It's keeping track of time. That battery keeps it going, and when you shut off power, it keeps track of time when you have a battery in there. So that's that guy. Well, and then, plus, we have some header pins. Let's see, where do I put those? Well, anywhere, but somewhere on here there are some I2C, well, I guess we just bring them out. So remember, we have that little prototype area down here. You could bring out some of these serial port pins to a prototype area, and you could talk to another chip if you'd like to. Technically, you could even take wires from our green board and wire another device that's communicating. You got to be careful. This SPI serial port and the I2C serial port are really not made for super long wires. Okay? These are more for close proximity devices that you communicate with. If you want to go over longer wires, there's other serial ports that are a little better for that. All right? Even in today, most serial ports, the one we always think about that can go over long wires is Ethernet. That's a big one. But like USB, you can hardly, if you start trying to go 10 feet with USB cables, you're going to start running into a lot of trouble. You can buy them that long, but you start getting issues and disconnects and all this kind of stuff. But anyway, so most of the SPI, most of I2C is all soldered on a board and close to your processor. Okay, so we need to figure out how we communicate with these devices. Okay? So the way I like to think about this, and let's just first focus on SPI today. So it's Serial Peripheral Interface is what that stands for. Okay? I always forget what anybody know what I2C is? Something interconnect or something like that. IC interconnect. I'll have to come up with, I'll have to find what that's abbreviation for by next time. But here we go, SPI. So the idea is, I like to draw it this way. We have our 28379D processor. And with SPI, we're going to see with I2C, they use different kind of pins. There is a pin called master out, slave in. All right? That's one pin that is going to be associated with the SPI. There's another one, master in, slave out. Okay? So master out, it always outputs data, so we could draw it that way. Master in is always bringing in data. Okay, bits at a time, right? Serial ports bring in 1 bit at a time, don't they? And then we collect those 1 bits to put together maybe 8-bit value or a 16-bit value. That's how serial ports work, remember? And then this guy, which is a little different. Remember, if you recall from the UART, remember the UART? We talked about that. It had a transmit and a receive, and then just ground, right? Those are only 3 wires for UART. In this case, you could kind of think of the master out being a transmit, right? And the master in being a receive, an RX. Anyway, okay. You'll also see this labeled, sometimes people label it SIMO. They just switch the SI and the MO. Or you'll see it SIMO or SOMI or whatever, like this. So you'll see it labeled a couple different ways. So that's those pins. Then we have this S clock, serial clock. And that can be labeled. Sometimes they call it just clock and things like that. But this is an output. The master, we'll talk about this idea of master and slave, but our 28379 is going to be the master of the SPI, serial port. And then finally, there is a pin that we set up as slave select. And that bar over the top means it's active low. Okay? So with these 4 pins, we can actually communicate, well, actually these 3 pins and then multiple slave selects, we can use pins to communicate with multiple devices. Okay, and in our case, on our green board, we have 2 chips that we're going to talk to. The DAN 28027, and then this MPU 9250. Okay? We could add more though, and that's what we want to kind of understand. There's a chip I really like for optical encoders called the LS7366. We'll be talking about that either today or tomorrow, Wednesday, sorry. But there's all sorts. There's some other nice devices. I like using this magnetic encoder, AS5145. In other words, there's all sorts of devices out there that can communicate over SPI, right? And you can talk to all those if you create an individual slave select for each of them. So what we're going to find, we'll have one maybe called slave select 0, and that will be associated, for example, for the DAN 28027, I have found that we can use GPIO9 is, oh, what did I do? Escape. All right, draw. Did it go away? There we go. GPIO9 we're going to use to slave select the DAN 28027. So this pin will go here. Then for the MPU 9250, it just turns out that I chose GPIO 66. And we could kind of call this slave select 1 if we wanted to. Oh my goodness, there we go. So, oops, slave select there. Now, we could use other pins. You saw last week that GPIO 52 is free. We use that to measure the time that we are inside our FIR filter code. Remember that? GPIO 52, maybe we call that slave select 2. Now, these are just names, right? The actual name of the pin is this right here. So we're just thinking of it as a slave select. We could use 52, for example, to select LS7366 chip out there, if we had it out there. Okay? What am I trying to get at? Well, this guy, to communicate with the DAN 28027, is different than communicating with the MPU 9250. They're different chips. They have different, again, we got that word registers. There's different setup registers in each of these devices. Okay? So you can only talk to one of these devices at a time. And the way we're going to do that is because it's active low, these slave selects, we're going to be manually, just like you turn off an LED, by saying GP data regs, GPIO data regs dot GP, in the case of GPIO 9, that would be GP clear, GPA clear, right, .bit.gpio9, right, that big long statement that we use to turn off an LED. And then to turn it on, we did GPA set. Agree with that? Remember doing that? Well, in the same way, turning on and off an LED, we're just going to turn off GPIO9, set it low to select the DAN chip, and then communicate to it. When we're done communicating to it in code, we will set GPIO9 high. So it's our way of saying, okay, I want to talk to this chip, then send the serial data across, then pull it back high. Okay? And when it needs to go high and low, that will be determined in the data sheet. It will tell us what to do. Does it have to be set low every 16 bits, every 8 bits? Or can it be set low and we send 16, 16, 16, 16? What needs to be sent, that's all found in the data sheet. Okay? Same thing, MPU 9250, we would have to have GPIO 9 high, GPIO 52 high, and only GPIO 66 low. When it's low, the MPU 9250 wakes up and says, okay, send me data. So that's why it's called the slave select. You're selecting which slave you want to talk to. Okay? And you do that manually. You have to, before you send over stuff to the chip, you have to pull that pin low. Okay? And so on. So we've got those slave selects. All right. Then, to send out data, okay? And this is always, you'll hear me say this over and over, and the lab will say this over and over again, because it's a concept that gets a little confusing. But you must send data to receive data on the SPI serial port. It does it at the same time. So when we're clocking out bits over to the device, we're also clocking in bits. And that's just what they chose for the SPI serial port. In other words, there is just one clock. There are other serial ports out there. There's a serial port that I just love that TI used to put in a lot of their chips. They called it the multi-buffered channeled serial port or whatever. MIC BSP is what it was called. And I used it a bunch in the past, but now TI decided not to put it in some of their devices. So anyway, well, you know, unwinding or whatever. But it had a clock for transmitting and a clock for receiving, which was really nice. Okay? In this case, with the SPI, there is just one clock. So you'll see, and I'm going to show you some MATLAB pictures, but let's first just think about this. So if we're looking at this on an oscilloscope, and we're going to talk about these different modes also, but when we do the digital channels, we're going to be able on our oscilloscope to have, you know, maybe D0 of our scope. That'll be our slave select pin for the whatever, for what we're talking to. And then D1 will be our S clock. Shoot, S clock. Why does it do that? I'm just CLK. And then D2, remember, D2, this is, you know, when we have our little scope probes for the digital channels, remember there's D1 through D7 is what I'm talking about. So we're going to be probing these on the launch pad. And then this is our master out, slave in. And then, for example, we probe master in, slave out. Okay. Now, what would happen is on the logic analyzer, we would see this slave select would go low. Okay? I'm just going to start it out. Then what happens, now we'll find out that there's different modes for this clock, but we're going to start out with the mode that a high going edge transitions data and we read data on a low going edge of the clock. So that's a little confusing. We'll get to that. But here's our clock going out. I'm gonna write this clock so I can do it kind of consistent here. And I'm gonna do, my erase does not work, huh? There we go. So we have 1 low going, 2, 3, 4, 5, 6, 7, 8. I'm going to go with that for now. So let's just imagine we're sending 8 bits of data, is what I'm trying to get out here. And receiving 8 bits, because we're doing both at the same time. So now, what are we sending? Let's just say we're going to send, who knows why, we're going to send the data OXC4. I don't know, whatever. Okay? What is that binary? That is 00100011. Okay? That's the data we'd like to send across for some reason to a device. Okay? So that device is out there. We pull the slave select low. That selects the chip. Then we want to send out this data. Well, I don't know if you remember from the UART, but the UART sent least significant bit first. Well, with the SPI and also with I2C, the most significant bit is sent first. That's whoever came up with this protocol made that decision. Okay? And so we've got to send a 1 first. So this clock tells us what to do. In other words, the master out pin could be low, it could have been high, whatever state it's in. Let's say it was low. On the transition high, this bit needs to be placed on the master out pin. So 1 needs to go to 1, the high state. Okay? And then it definitely needs to be high when we go low, when the clock goes low. That is the instance when the S serial port on the slave device will read in that 1 bit, or on the master in pins when we read in data on that pin. So let's just continue. So that sits at 1, and then it stays at 1. So I'm going to draw this line right here, because this is where it's what it's outputting. All right, and then we transition on the high to go low. So we stay low, another low, and another low. Right there. So we've got, right now we've got a 1 going out, another 1, a 0, a 0, a 0, and then we've got a 1 here, and then back down, 0, 0. Right? All these edges, all these down-going edges is when we look at the data to see what's on the pin. Down edge, down edge, down edge. So this is a 1 and a 0 and a 0. Kind of see what I'm doing there? Now, of course, this master out pin and the clock, you know, we have to manually move slave select low in your code. So there's going to be a line for us to write slave select low. What we don't have to do is transition the clock high and low, high and low. We don't do that. The serial port has all control over the S clock. It also has all control over the master out pin. Yeah?
Does the clock just constantly run, like you have the flats, but like would it just go up and down like continuously?
It does not.
Oh, okay.
Yeah, the clock will only run while it's shifting out data. It has a default state. So now if you were right away going to send another 8 bits, yes, it would continue clocking. But whenever it's done, so let's say you told it to write out 8-bit values. It would clock for 8 times 8, right? 64 clocks, and then it would go back to its initial state and stay there. There are some serial ports that just keep on clocking. You're right. Yeah. Anyway, and you would ignore it when slave select is high. That clock would be ignored. Yeah.
So is it only allowed to send a byte of data every time?
That's right. So yeah. And you'll find in the data sheet, you know, like for the MPU 9250, that the IMU, you need to get a bunch of data from it. You can get gyro data, you can get accelerometer data, you can get compass data. So you'll be sending a bunch of clocks, but once those are all done, yes, that list of data, and then the clock goes back to its default state. You know. Good. All right. that's happening now. You guys help me out. Let's just draw here, because master in, that's coming from the slave. So the master doesn't have control over what data is coming into it. That's being controlled by the slave device. Okay, so let's just try something here. What if I go, let's see if I can do the transitions right. Let's see, so on the high gown edge, if I just say it does this, it's hard to draw. That's why I have some MATLAB drawings here. Let's see what happens here. Okay, so what you would do in this mode, let's see what data that is right there if I drew it up right. We would look at this data, the master, when it's bringing in data, in this mode, whenever the clock is going low right here. And so there's 1, 2, 3, 4, 5, 6, 7, 8 places where it's going low with that clock, right? So the master, whenever that happens, the slave, okay, so what about this mode? How do you know that we read data on the low going edge? You got to look at the data sheet of the slave device. Okay? So this is like not necessarily not plug and play in a sense. You have to go read a data sheet to figure out, because you can change the mode of the SPI to read data on the rising edge of the clock if you want. Anyway, so those are just things you have to go, and we'll show you that in data sheets. But for now, we're assuming that the slave uses this mode, and so what we would be getting is on this edge, we draw up a line, there's a 1, and then we draw up here, and sorry, that's a 0, 0, and this is a 1. Up here, there's a 1, 1, 0, 1, 1, 0. See what I did there? So that happens to be, with my little sketch there, what came into the SPI serial port. And again, we're getting most significant bit first, so that means we're reading in 7, 6, hex 76. No. Yeah, that's right. 7, 6. Yeah, exactly. Hex 76 just happens to be what I drew there on the board. Okay, on that. Is that making some sense? A little bit, huh? Okay. So, and then it would continue. But if all we were doing is communicating 8 bits of data from this device, this is a really simple transition, what we'd have to do after we've received this hex 76 in code, we'd have to pull the chip select back high. Okay? So we'd have to do a GPA set, for example, if we're using GPIO 9, right? And that would set that pin again. Okay. So you're going to be seeing things like this on the oscilloscope. This is what I want us to get to this week. Is big. Make sure we're seeing what the SPI looks like on the oscilloscope. And that's one of the reasons I really like, if I was going to choose, if I had a device that could use both SPI and I2C, I usually choose the SPI serial port. One, the main reason, well, it's a little bit faster, that's probably the main reason. But the other reason is it's so much easier to debug compared to I2C. And you'll see that. If you write to the wrong address in I2C, the I2C just hangs. And sometimes it can be pretty hard to figure out what's going wrong. So, but once you get I2C working, it's a very nice interface also. And more for slower devices. SPI's clocks can go, usually most devices are around 1 megahertz to about 5 megahertz clock speed. But there are high-speed SPI devices out there that can go 20 megahertz clock and even faster than that. So, but anyway, and then I2C, which we're going to get to next week, its maximum rate for at least the kind of standard I2C is about 400 kilobits per second. So anyway, so we'll talk more about that. Okay, so we have this protocol here. All right. Now, what you'll see me doing in using MATLAB to draw these, instead of me having to draw all that manually, you saw how tedious that was, you're going to see that I produce these kind of graphs to kind of talk about this. And these are, now, they're not quite this blown up, but you'll see, I'm going to show you some data sheets. They do have little tables, little pictures called time load graphs, right, to kind of show you what needs to be sent across to this device in order that you receive the correct data. Okay, so we'll be looking at these and trying to decipher these to understand what needs to be sent when and all this good stuff. But notice here, the way this one is set up, and depends, again, you'd have to check the data sheet for this device, whatever it is that I've put up here. Notice, according to my timing diagram, it needs a chip select low and then high for each of the 8 bits. Now, I've seen some devices that can handle this. Most of the time, though, when we're sending across this much data, one right after the other, you just pull chip select low and keep it low until you're done with the chip. Okay? And so let's see if I have an example there. That would look like, I have one here. Oops, what am I doing? CD. Let's see if this one does it. Yeah, 1 pulse. Oop, should have had this pulled up. Let's see, 1 pulse. There we go. Let's run this. Did I get an error? Oh, well, okay. What else do I have? SPI mode 01 1. Let's see if this one will work. Of course not. So I haven't set baud or something. All right, fine. Baud equals. Oh, that's why I'm not passing it the right things. My bad. Oh well. All I'm doing is trying to get that pulse to stay down. So let's see here. Create plot. That's my bad. That's what I'm doing wrong. Create plot SPI. See if this one does it. There we go. Okay. All that to just get this one thing to stay low. But, so there, right, slave select stays low for the whole data transmission. And in this case, we're going to find, actually with the DAN 28027 chip, that it's looking for a chunk of 16 bits, and then another chunk of 16 bits, and then another. Okay, so you're sending across 3 16-bit words, or 16-bit ints, whatever you want to think about it, over to the device. Okay. Now, also, when you're sending, you're also receiving data. Okay? Both of these things are going up across here. Now, notice that sometimes, and we'll call it garbage or whatever, due to this protocol that we're sending and receiving at the same time, sometimes we'll send something across, and while that part of the communication is being sent across, we're getting back something, but it's of no use to us. It doesn't have any information for us. It's just setting, most of the time that'll just buy a bunch of zeros. Okay? So the issue though is you do receive this. This comes into your 28379D serial port. So there is a spot where we have to read this, but we just don't use it. Okay? And that becomes a little confusing. That's where we got a lot of little confusion points with this serial port, so we have to watch out for that. Some devices make it kind of more like so the idea is, we have transmissions that are, well, first we talk about synchronous and asynchronous. Asynchronous, right, doesn't have a clock. So this is a synchronous serial port. And then we talk about duplex and half duplex. Maybe you've heard of that before with serial ports. Duplex means you're sending and receiving at the same time. This would be duplex, can be duplex. Half duplex is you only can send, and then the next thing you do is you receive data, right? You can only be sending or receiving. So I squared C we're going to find is half duplex. You can only be sending data for the clock bits, or you can be reading, bringing in data. So that's that. So sometimes in data sheets, and we'll see this, when we send across data, nothing is coming back of importance, or at least when we're sending over information to the chip, nothing is coming back to us that we need. The issue though is even though we're getting data we don't need, we still have to read it. We have to remove it from the serial port's device, from the peripheral, this SPI peripheral. So we got to keep that in mind. So we'll have like garbage int or something like that, and we'll have our temp int, and we'll have to read that data off what we call the FIFO. We'll get to that. We have to do that. Then, when we want to read data on some of those devices, we just send over garbage. In other words, we just send maybe a command saying, I want to read the data, and then if it's 4 16-bit values, you send 0, 0, 0 when we're receiving that good data back. So again, this is just a protocol. So, it's the idea of, you getting together and say, how are we going to communicate with each other? All right, we're going to come up with this protocol. We're going to, when you want to receive data, you're going to send over the command 2 or whatever. When you want to, when this data needs to go to this register up here, you're going to send over the data first 3, and then it'll go up to that point. It's a little more complicated than that, but that's where we have to go look at the data sheet for that information. Okay. So let's do that. Let's look at a data sheet. This one's a pretty good one here. Let's go to this chip that I like, the LS. It's not on our board, but where's my folders? Let's go here. Come on. Here we go. So this LS7366 chip. Again, you won't be using this in lab, but it's a nice one. I think the data sheet does a pretty good job of showing you what the protocol and all that. So all this you already have this device inside the 28379D processor. It's just a quadrature encoder counting chip. And we're going to be getting to quadrature encoders real soon. Lab 6, I guess, we'll be talking about. But this would be a way to communicate with an optical encoder, bring us that sensor into your chip if you didn't have the device inside your processor. But anyway, we kind of march down here, and it's got a couple registers of its own. Okay, so let's just kind of write these down. We've got a flag register. We've got this RLD register. We've got a CMR register. Okay, let's just go with those. Let's just talk about those 3. And an IOR register. Great. So back here. So now, again, we've got our 28379D, and it's got the SPI serial port. And those 4 pins are coming across. And then we've got this chip over here, the LS7366. Now, when we wire this up, just like before, this is its master out, slave in. So that means it's going this way. It's got, and the neat thing with SPI, usually they label the pins the same and they just match up. You don't have to like oops, other way, wouldn't it be? So it goes. Why does it do that? I'm having all sorts of trouble. I'm going to figure this out. Sorry, folks, having trouble today. So not an arrow there. I can't erase for some reason. That would go that way. And then we have our clock. That's going this way. And then we have our slave select going this way. Okay. Now, again, this being a slave, this being the master. Okay. Now, inside here, inside the chip, there are some registers we need to talk to. What did we say? One's called the IOR. What was the other ones? We've got an IOR. We've got a CMR. We've got an RLD. CMR. RLD. And finally, whatever. What was that last one? Flag. I forgot that one. Okay, flag register. Okay. Now, we need to communicate to these different registers. Well, to do that, we can look at this data sheet and try to understand its protocol. Well, let's see if we can find this. Here we go. So to write to the XIOR, etc., you would do this. In other words, so we got to get to this. We're digging down, but in other words, it's trying to explain how do we write to these different registers by setting these data pins. We got to figure out what that means: D7, D6, D5, and then we've got this control data bit. All sorts of great stuff for communicating to this thing. Oh my, I'm just having a great day. This is the wrong data sheet. This is for, I was wondering, this didn't look right. That is for the 7266. I wanted the 7366 data sheet. Sorry, folks. It's very similar, but here it is, 7366. I pulled up the wrong one. All right. So a little bit different registers. There's a status register, STR. Okay, anyway. So, back to this. So, here was the instructions to talk to we have a master register, we got a DTR counter register, an OTR register. We need to talk to all those things. Okay, and to do that, you kind of search through this, but there are these timing diagrams that show you how to do some of this. Okay? And that's what I was trying to get to. But now, by looking at this and reading the text up above, their hope is that you understand how to talk to this device. Okay? And we'll get into this more. We'll look at other data sheets, and of course look at the data sheets that you'll be using in lab. But notice, remember I talked about random data garbage being sent across? X's right here mean don't cares. Right? We've seen that before in the data sheets, right? So, looking at this, what needs to happen? Okay, well, if we want to write to the MDR register, okay, there is a command that we need to send, these 8 bits right here. Okay, this is just for this device. We notice here, remember I was doing data, the mode where when you when the clock went low, data was written, was read by the device. Here, it's when it's going high. In other words, it's in the middle of this bit set high. So that mode's a little different. We'll come back to that also on Wednesday. But here, we pull slave select low, and then we start clocking out data on the master out pin. Notice here, this right here, this line is meaning nothing of importance is coming back in on the master in pin. It's probably 0, but who knows? So we are reading that in while we're writing out, but it's garbage to us. We will discard it once we've read it out of the serial port. Okay? And so during that 8-bit transmission, we're getting back nothing of importance, but we are telling the device, hey, I want to write to this master data register. And what do I want to write? I want to write this 8-bit command right here. Okay? Anyway, yeah, I don't know what that don't care, that just meant it wasn't clocked, so I don't know why they have that don't care there. But anyway, we want to write out this data, fine, okay? And then, if we want to issue, notice, and then chip select goes high, so we're done. We've just issued the command to write these settings to the master data register. Okay, you don't even know what that means, but we just know that it's out there and we need to write data to it, okay? We would have to look at the data sheet to see what makes sense, what data bits 0 through 7 make sense to write to that device. That would be in the data sheet. But anyway, okay. But then, all right, now maybe I want to write it out and then just check that it got to the right value that I sent. Who knows? Do some nice error checking, okay? So again, we would pull the chip select low again and now issue a command to read the MDR1 register. Now look what happens. It's a different command. Look here, when we did a write to it, we sent, X's will just make 0. We made it 0, 0, 0, 0, 1, 0, 0, 1. What we would find in the data sheet, that means write to MDR1. Someone came up with that protocol. To read, instead, now it's 0, 0, 0, 0, 1, 0, 1, 0. So these two flopped, 7 and 6. That's the command to read the MDR1 register. Okay, now what do we have to do? We have to send across this 7 bits, which was 0, 0, 0, 0, 1, 0, 1, 0, which is 5, 0. Hex 550 is what you're sending there. And then, look here, this is always get you. You've got to write something to receive something. So the data sheet's saying random data. That's right. It could be anything. You could write all 1s. You could write all 0s. It doesn't matter. It's got to be something written because we must write to read on an SPI serial port. So the first thing we read is garbage, but the next 8 bits we get is actually what the MDR register is set to. Okay? All right. We'll keep on talking about that. It is confusing. Another reason we give you 3 weeks for these labs, but we'll continue on that on Wednesday.